In this video, we're going to be talking about properties of special parallelograms. So getting more and more specific with each type of shape that we've talked about in the last few videos. Talked about quadrilaterals, and then we got a little bit more specific and talked about parallelograms. Those are types of quadrilaterals. And then now we're going to talk about special types of parallelograms. So even more specific still. So these shapes that we talk about today are going to be inheriting the quadrilateral and parallelogram properties. And in addition to those properties, they're going to have their own unique special properties, making them specific types of shapes. For example, we have a rectangle, which is a special type of parallelogram. Not only is it a quadrilateral, it has four sides and all four of its angles inside add up to 360, but it's also a parallelogram, meaning that opposite sides are congruent, opposite sides are parallel, opposite angles are congruent, same side angles are supplementary, or consecutive angles are supplementary, and diagonals are going to cut each other in half or bisect each other. In addition to those properties, what makes this a rectangle rather than just any other parallelogram are these two special properties right here. In a rectangle, all angles are congruent. All its interior angles are congruent. They're all 90 degrees. So we could put boxes to symbolize that in our diagram. And diagonals are not only bisecting each other, but they're congruent to each other. So this entire diagonal length is the same length as the other diagonal's length. So if we cut those in halves, then we have four equal halves. They're all equal. So those are the two properties making it a rectangle. Be careful though. These diagonals are not bisecting that 90 degrees. They're not cutting the right angle in half there. That happens in different shapes, not rectangles. Another important thing to note is that a rectangle is created by four different isosceles triangles. So we can use properties of isosceles triangles in rectangles to help us solve for some unknown measures sometimes. Let's practice using these properties to solve for these unknown measures in rectangle BART, B-A-R-T. So based on this initial value or initial condition, angle 1 is 38 degrees. Let's try and figure out these values. If angle 1 is 38, angle 2 has to be 38 because this is an isosceles triangle. And these are the base angles of those triangles. They are congruent. Angle 3 is going to be 52 degrees because this corner right here at angle A is a right angle. It's going to add up to 90. So if I subtract angle 2 from 90, or do 90 minus 38, then I get the measurement of angle 3, which is 52. Over here in this isosceles triangle on the right, angles 3 and 4 are base angles again, so they must be the same. So angle 4 is 52. And to solve for this diagonal piece right here, all of these diagonal pieces are going to be 4 inches, so x must be 4. If we wanted to talk about the entire diagonal length, we would just double this, and the entire diagonal length is 8. So there's a rectangle. Let's talk about another special type of parallelogram. It's called a rhombus. And a rhombus is also a quadrilateral and a parallelogram, so it inherits all of those properties. But what makes it specifically a rhombus rather than, say, a rectangle is these three properties. All sides are the same or congruent. So all of the side lengths are all the same in a rhombus. The diagonals are perpendicular to each other. Perpendicular lines create right angles. So all of those angles in the middle there are going to be right angles. And in most diagrams, they only give you one of those boxes because they assume that you can imply that all of them are right angles. The last property, diagonals bisect vertex angles. So that didn't happen in a rectangle, but it does happen in a rhombus. These diagonals are going to cut the corner angles or vertex angles exactly in half, or into two equal halves. The triangles that make up a rhombus are just right scaling triangles. They're definitely right angles or right triangles because of those right angles, but none of the sides in each of those triangles are the same, so they're going to be scaling. Let's see if we can use those properties to solve for missing pieces of a rhombus. Again, we're given some initial condition. Angle 1 is 35. Let's see if we can use that to solve for the other missing pieces. If angle 1 is 35, angle 2 must be 35 because this angle gets bisected by that diagonal so that both of those angles are exactly the same. If angle 2 is 35 and we have a right angle in this triangle, then we can use that information to solve for angle 3. If I know that the three angles in a triangle add up to 180, well, then I can just subtract the measurement of angle 2 and this right angle from 180, and I can get the measurement of angle 3. There is another way we could think about it. We know that same side angles are supplementary in parallelograms, so all of these top angles must add up to 180. Well, angle 1 and angle 2 add up to 70. If we subtract that from 180, we know that this entire angle over here has to be 110 degrees. And if we bisect 110 or cut it in half, then each of its halves are 55 degrees. So if angle 3 is 55 and angle 4 is 55, then the entire angle E must be 110 degrees. Angle 5 is just vertical from that right angle. Vertical angles are congruent. All of these angles in the center here are 90 degrees. So angle 5 is 90 degrees. And the side length, represented by x here, all the side lengths in a rhombus are equal, so all of these outside lengths are 8 feet. So x must be 8. So there's a rhombus. We got one more special type of parallelogram. It's called a square. And squares are the most complicated of all parallelograms. They're the most special because they actually inherit every single property that we have talked about. They are a quadrilateral, so they have the quadrilateral properties. They are parallelograms, so they have all the parallelogram properties. But they also have all of the rectangle and rhombus properties. In addition to all of that, the triangles that make up a square are actually right isosceles triangles, which we know as 45, 45, 90 right triangles. So we can also use those properties to help us solve a square. So lots going on in a square. Let's see if we can use all those properties to solve for some unknown measures. Given the condition that angle 1 is 45 degrees, well, that's always true in a square because the diagonals are always going to bisect those corner angles. It gets that property from the rhombus. So if I bisect 90 or cut 90 in half, each of these halves must be 45 degrees. So angle 2 is 45. Angle 3 must be the same, 45. Angle 4 must be 90 because just like in a rhombus, these diagonals are going to be perpendicular. All of these center angles are going to be 90 degrees. Angle A is talking about the entire angle over here. Each vertex angle in a square is 90 degrees or a right angle. So the measurement of angle A is 90. It gets that property from a rectangle. To solve for x, we have to use the properties of a special 45, 45, 90 right triangle. If we just look at this triangle, we know that the legs are equal and that the hypotenuse is the leg value times the square root of 2. So x must be 12 times the square root of 2. We could also use Pythagorean theorem to get there as well and use a decimal value. And then y is just saying that legs are equal, so the diagonals are all 12 each of their halves are 12.